Swayam Prabha. Digital India. Educated India.
Good morning, everyone. So, we are looking into the matrices, determinants, eigenvalue problems and their applications in various chemical engineering problems. So, in the last class we looked into the standard eigenvalue problems, and there are various properties of an eigenvalues and eigenvectors of a square matrix would satisfy, and we are looking into some of these properties and we have derived several theorems for that. The last theorem, as I remember, is that we have proved that for a symmetric matrix the eigenvectors are orthogonal to each other if the eigenvalues are simple. That means, all the eigenvalues are distinct. Now, in this class we will look into one more theorem that will be quite appropriate, and it will be quite useful as we go along this course, various classes of this course. This theorem is the last theorem that we are going to look into the series of theorems that of an eigenvalue problem should satisfy, and after this we will be looking into some of the typical major applications of eigenvalue problems in chemical engineering applications. Now, this theorem is that for the eigenvectors for a matrix and its transpose matrix, they are orthogonal to each other. They form a bi-orthogonal set. We have already seen earlier that the eigenvalues of a matrix and its transpose matrix are identical, and but their eigenvectors may not be identical. So, in this theorem we will be proving that eigenvectors of A and A transpose, where the matrix is A, they are mutually orthogonal to each other and form a bi-orthogonal set. So, the last theorem that we are going to prove, which deals with properties of the eigenvectors, is that eigenvectors of a matrix A and its transpose matrix A transpose, they form an orthogonal set. So, we formulate the corresponding eigenvalue problem. This problem is A x I is lambda I x I, that is number 1. Next one is A transpose y j is lambda j y j. So, okay, this is y. This is the eigenvalue problem for the matrix A, and this is the eigenvalue problem for the matrix A transpose, where x i's are eigenvectors of matrix A and y j's are the eigenvectors of matrix A transpose. So, next what we do? We take the left inner product of equation 1 with respect to y j and see what we get. Take left inner product of equation 1 with respect to y j, and what we will be getting is that y inner product of y j A x I is nothing but inner product of y j lambda I x I. So, if you remember the property of the inner product, and that we have already proved this earlier, that is inner product of y j and x j will be nothing but multiplication of y j transpose and x j, that we have already proved earlier. So, utilizing this we will be simplifying the left hand side of this equation. So, this equation, so it will be nothing but y j transpose multiplied by a x I. So, if we get that, we will be writing y j multiplied by a x I should be is equal to inner product of y j and lambda I x I. Now, we have already looked into the property of inner product, since lambda I being an eigenvalue, it is a scalar. So, this scalar will be coming out of the inner product sign, and it will be y j and inner product of y j and x I. So, this is equation number 3. Okay. So, next we will take the inner product of equation number 2, that is the eigenvalue problem of A transpose with respect to x I. So, we take right inner product of equation 2 with respect to x I. If we do that, what we will be getting is that inner product of A transpose y j and x I should be is equal to inner product of lambda j y j and x I. Now, using the same rule that we have already theorem that we have already proved earlier, this will be nothing but multiplication of transpose of A transpose y j and x I. So, if you write it that way, you will be getting A transpose y j transpose of that x I is equal to, again here the lambda j being a scalar. So, it will be coming out of the inner product. So, it will be y j comma x I. Now, we invoke the property of the matrix operation, that is A B transpose is nothing but B transpose A transpose. Invoking this property and utilizing it over here, what we will be getting is y j transpose and A transpose of that x I lambda j inner product of y j and x I. So, you will be getting y j transpose of transpose. So, it will be A transpose and entire A transpose should be is equal to lambda j y j x I. So, this will be y j transpose of transpose will be the same. So, it will be y j transpose A x I is equal to lambda j y j comma x I. So, if you look into the earlier derivation, that when we take the left inner product of equation number 1 with respect to y j, so it will be inner product of y j and A x I is equal to y j inner product between y j and lambda I x I. We invoke this property, inner product of y j and x j should be y j transpose and x j. So, in this equation we will be having a transpose over here. So, that is equation number 3 and this is equation number 4. Now, if you compare the equation between the equation number 3 and 4, you will be seeing that the left hand side is identical. So, therefore, comparing the two, we can from 3 and 4, equation 3 and 4, we can say that lambda I inner product of y j x I is equal to lambda j inner product of y j x I. So, and we have already seen that inner product of x and y is identical as inner product of y and x. So, we utilize this property and come to the conclusion when you get this on the left hand side, what you will be getting. So, basically inner product of y j and x I is identical to the inner product of y j and x I. So, you will be getting lambda I minus lambda j inner product of y j and x I is equal to 0. Now, this lambda I is not equal to lambda j. So, therefore, we will be having to satisfy this equation, the only option we have that inner product of y j and x I is equal to 0. That means, the eigenvectors of A transpose and eigenvectors of A, they are orthogonal to each other. So, y j and x I are orthogonal to each other, provided I is not equal to j. So, this will be satisfied if I is not equal to j. So, this set of the eigenvectors of A and eigenvectors of A transpose, they are called to form a bi-orthogonal set. So, if we talk about a vector in R3 space, a matrix in R3 space. So, it will be a 3 into 3 matrix. A is basically have a size 3 into 3 and it will be having the eigenvectors x 1, x 2 and x 3. Similarly, A transpose will be having eigenvectors y 1, y 2 and y 3. Then by using this theorem, one can say that inner product of x 1 and y 2 is equal to inner product of x 1 and y 3 is equal to inner product of x 2 and y 1 is equal to inner product of x 2 and y 3 is equal to inner product of x 3 and y 1 is equal to inner product of x 3 and y 2 will be is equal to 0. That means, unless and until I is not equal to j, all the eigenvectors they form the bi-orthogonal set and they will be orthogonal to each other. So, that completes this proof that A and A transpose, the eigenvectors of A and A transpose will form a bi-orthogonal set and these eigenvectors will be orthogonal to each other. Okay. So, that completes various theorems of a standard eigenvalue problems, where the eigenvalues and eigenvectors will obey these rules or axioms. Now, next what we will be doing, we will be looking into several chemical engineering applications of these eigenvalues and eigenvector problems. So, let us look into the applications in chemical engineering problems. Okay. The first application I will be talking about is the solution to non-homogeneous set of algebraic equation. Whenever we will be writing the mathematical models for any chemical engineering systems, typically for a steady state problem you will be landing up with a set of algebraic equation. In case of transient problems you will be landing up with a set of ordinary differential equations. Now, both of these set of equations, either algebraic equations or ordinary differential equations, they are typical for any chemical engineering processes depending on the steady state and unsteady state. Now, using these eigenvalue problems one can elegantly solve this set of equations. So, we will be using this method or the eigenvalue method as a tool to solve various chemical engineering problems. Now, we will be looking into the solution of set of algebraic equation algebraic equations. These are typically correspond to steady state problems. Steady state situation. Okay. So, we need to solve a set of equation in a compact form, the compact notation, compact form or notation, matrix notation. This set of equations is written in this form: A x is equal to b, and this term b on the right hand side is the source of non-homogeneity, and therefore, these equations are called non-homogeneous algebraic equations. Now, the vector x belongs to n dimensional real space. We formulate the whole problem in a more generalized fashion, so that it can be reduced to solution of any dimensional finite dimensional problem, maybe 3 dimensional problem, maybe 10 dimensional problem. And similarly, the vector b belongs to n dimensional real space, where the matrix A is having a size n into n. Now, out in this equation 1, A, B are known, both A, B are known, because whenever you are writing, you are modeling the chemical engineering process, what you are basically doing, you are writing some mathematical expressions to express the chemical engineering processes. So, that is called the modeling. Solution of them is the simulation. Now, the matrix, the various elements of the matrix A will be determined from the process, and we will be looking into a specific example of this. And similarly, from the model equations, the various elements of this vector B will be known. So, A and B are known, they are fixed by the process of the chemical engineering process. On the other hand, the solution matrix, the solution vector x is not known. Okay. So, therefore, where our aim is to obtain this vector x. Now, we consider, so what is the method that we are going to adopt? We consider matrix A and the set of vector x, say a set of vectors x I, which are basically constitute x 1, x 2, x 3 up to x n. They are eigenvectors of A, which are, so set of vectors A x 1 to x n are the eigenvectors of A. And of course, we have already proved that eigenvectors of a matrix are independent to each other, and they form a basis set. So, therefore, we already proved that eigenvectors of a matrix A are always independent, they form independent set of vectors. So, therefore, they form a basis set. That means, any other vector in the space can be written as a linear combination of these eigenvectors which are independent vectors. Therefore, this the vector B in equation number 1 can be expressed as a linear combination of eigenvectors which are nothing but eigenvectors of the matrix A. So, let us express the vector B as a linear combination of eigenvectors I is equal to 1 to n. So, since xi's form the basis set vectors or independent set vectors. So, therefore, the vector B can be expressed as a linear combination of this. Okay. So, the coefficients beta I are not known to us, we are going to determine it. Now, let us consider another case. Let us consider the set of vectors y 1, y 2, y 3 up to y n are eigenvectors of A transpose. A transpose, and since these are also eigenvectors of a matrix A transpose, they form a set, they form a basis set. Now, next what we do? We take the inner product of equation A with respect to, let us say, any eigenvector of A transpose, let us say with respect to y 1. Take inner product of equation 1 with respect to vector y 1. So, what we will be getting is that y 1 inner product of y 1 and b will be nothing but summation, because if you just express it, you just open up this summation term wise, then it will be inner product of each term with respect to y 1. So, we can take the put the summation outside, and this will be simply I is equal to 1 to n inner product of beta I x I and y 1. So, these will be nothing but I is equal to 1 to 1 and beta I being a scalar. So, it by the property of inner product, it will be taken out of the inner product sign, and this will be simply x I and y 1. Now, we open up this summation. So, this sum, if you open up this summation, this will be become beta 1 inner product of x 1 y 1 plus beta 2 inner product of x 2 y 1 plus beta 3 inner product of x 3 y 1 likewise, and finally, you will be having beta n inner product of x n and y 1. And we have already seen that for the two matrices in this class, the first theorem that we have proved in this class, that for the matrix A and A transpose, the corresponding eigenvector will form a bi-orthogonal set. So, therefore, x I and y j inner product of that will be always equal to 0 for I is not equal to j, where x i's are the eigenvectors of A and y j's are the eigenvectors of A transpose. Therefore, will be all these terms will be equal to 0, x 2 inner product of x 2 and y 1, x 3 and y 1, x n and y 1. Only one term will survive out of the summation series, and that will be beta x 1 and y 1. So, inner product of x 1 and y 1. So, you will be able to calculate the value of beta 1, that will be simply y 1 inner product of y 1 and b and inner product of x 1 and y 1. So, you can write it in more compact notation y 1 transpose b and x 1 transpose y 1. So, it will be matrix multiplication. So, therefore, this whole thing can be calculated as beta 1. So, you can generalize it and we will be able to get the form of beta 1 as y 1 y I transpose b and you can write it as x 1 transpose y 1. You can put it in the notation I, and you can always argue that x 1 inner product of x 1 and y 1 is equal to inner product of y 1 and x 1. So, what is x 1 transpose y 1? That will be identical to y 1 transpose x 1. So, therefore, since this is in the form of y j transpose, we can write it in this form in a more generalized fashion y I transpose b divided by y I transpose x I. Sorry, this will be y, this will be y. So, they are identical. Inner product of x 1 y 1 is equal to inner product of y 1 x 1. So, inner product of x I and y 1 is identical to inner product of y I x I. Why we have written in so they are basically identical. Why we have written in this form? Because here it appears this transpose, here it is appearing as y I. So, I would like to put as y I t and x I. Why I will be doing that? I will just come in a minute that whenever you will be having a large number of system, large dimensional system, for example, a 10 into 10 dimensional system or maybe a 20 into 20 dimensional system, it is a very complicated system. So, you will be tackling with so many equations simultaneously, then you cannot calculate all these things by using a calculator or by hand. So, you have to take recourse to the numerical techniques. So, if you put it in this form, the numerical operations will be more. So, for numerical, if you talk about the numerical calculations, what is basically doing that? You will be doing that, you will be taking recourse of simple assumptions, simple operations in order to compute beta I. To compute beta I, what you have, the operations you have to take, you have to basically get, once you have the have a vector, you have to get the transpose of the vector. How the transpose of vectors will be done? It is very simple operation. It is basically the rows will be the elements in the rows will be or columns will be assigned to those in the rows. So, therefore, by changing the indices, one can get a transpose vector, maybe y I to y transpose. Is basically you just write, it is a one line program. Next is the multiplication of the two vectors or two matrices. This is 1 into n, this is n into 1. So, you can have a matrix multiplication, and this matrix multiplication, if you remember, it is basically multiplying the corresponding terms and then add them up. Okay, you multiply the corresponding terms and add them up, and that will be giving the value of the multiplication of the matrices. So, it is basically the basic operation is multiplication. First is multiplication, second is addition. You multiply the corresponding elements and add them up. So, therefore, once you get this operation y I to y transpose. So, by writing one simple 1 or 2 lines simple subroutines, you need not to compute x I transpose. So, what is the advantage you are going to get by writing it in this form? The advantage is that once you are writing a program for getting the value of elements of y I transpose, you need not to compute the elements of x I transpose. Same y I transpose will be appearing in the denominator and the numerator. So, you avoid one more subroutine which will be calculating x I transpose. So, that is not required, that is why we have written this this equation, keeping the denominator in the form of y I transpose. So, that same transpose routine, since all the elements of y I transpose have already been computed, that can be directly used here, and we have reduced one step of computation. So, therefore, it is a known vector B, and x i's are known because they are the eigenvectors of the matrix A. Y i's are known because they are the eigenvectors of y transpose. So, we will be able to compute the values of beta I. So, beta i's will be calculated from this equation. Now, if you remember that in our original problem, our aim is to calculate x in equation number 1. Our aim was not to calculate beta I, but our aim was to calculate x, the solution vector in equation 1. And what is x? It is nothing but the solution vector. Now, since again this vector belongs to n dimensional space, again this vector can be written as a linear combination of eigenvectors of A trans of the matrix A, because they form a basis set of vectors. So, therefore, x can be expressed as a linear combination of basis set vectors which are nothing but the eigenvectors of matrix A. So, therefore, we can write x can be written as I is equal to 1 to n alpha I x I, and so this is one more equation. And then what we do, since matrix is an operation, we take we operate this equation by A. So, whatever we will be getting is that A x is nothing but summation of A alpha I x I. So, alpha I can be taken as alpha is being a scalar. So, it will be operated on every vector. So, it will be nothing but summation alpha I A x I. And if you remember what these x i's are, these x i's are nothing but the eigenvectors of the matrix A. So, they will satisfy the equation A x I is equal to lambda I x I. So, A x i's will always satisfy the corresponding eigenvalue problem. This is the eigenvalue problem of A of matrix A, where lambda I are the eigenvalues and x i's are eigenvectors. So, therefore, we can write this equation as A x is equal to summation alpha I lambda I x I. So, this is equation number 3. Similarly, we have the, if you remember what was our original problem, the original problem was a set of non-homogeneous equations. So, A x is equal to B. So, therefore, we just substitute A x by this equation. So, this will be summation alpha I lambda I x I, and this B, if you remember from equation number 2, we have written as B as a linear combination of the eigenvectors x I. So, this will be nothing but beta I x I, where the index I runs from 1 to n and 1 to n. So, therefore, we can take this on this side. So, this will be alpha I lambda I minus beta I is equal to multiplied by the vector x I is equal to 0, where the index I runs from 1 to n. Now, since x I forms an independent set of equation or independent set of vectors. So, they are members of a basis set, they are all independent. So, therefore, to satisfy this equation to be 0, all the coefficients have to be identically equal to 0, and we have already proved this earlier. So, therefore, to satisfy equation number 4, one has to have the corresponding coefficient should be equal to 0. So, alpha I lambda I should be is equal minus beta I should be equal to 0. So, therefore, the condition that we are going to have to get this equation correctly, we have the alpha I is equal to nothing but beta I by lambda I. So, therefore, we will be getting what is beta I? Beta I we have already proved that it is nothing but y I transpose b divided by lambda I. Lambda I will be there, y I transpose x I. So, this will be the expression of alpha I, and if you remember what these alphas are there, alpha your solution vector is formed by alpha I x I. So, this is the solution vector that we are looking for. These are the eigenvectors of A. So, these are known. Alpha I are the corresponding alpha I is obtained from this equation. So, where in this equation B is a known vector, y I are the eigenvectors of A transpose. So, again this is a known vector. So, the numerator can be computed. Lambda I are the corresponding eigenvalues of A. Eigenvalues of A and A transpose both are identical, we have already proved that. So, this is also known, numerator is known, and xi's are basically the eigenvectors of A, they are also known. So, alpha I can be computed. Once alpha I is known, by using this equation you can xi's are known and alpha is known, you can get the solution vector x. So, therefore, this is an elegant way of getting the solution of set of algebraic equation. So, let us look into what are the different subroutines one has to make to compute this problem for solution of this problem numerically. Subroutines one has to write are as follows. First one is that you have to have a subroutine to get a first you have to get the subroutine to get the eigenvalues. Subroutine to compute the eigenvalues of a matrix, and to get the eigenvalues you will be getting a characteristic equation, and from that characteristic equation you can find out the using Given's equation using the Horner's method one can find the number of roots in a polynomial. So, basically you will be getting a root finding, subrouting, get roots or zeros of a polynomial. Next, corresponding to these eigenvalues, you have to have a subroutine for eigenvectors. Maybe there are several methods, Given's method is one of them. So, you can compute the eigenvectors. Then only these two are the major things, then you have to write a program which will get a transpose matrix from a matrix, convert a program that converts A to A transpose, that is again a small program, couple of lines program maybe. Then second, a program for summation for matrix multiplication, next you have to get a program for addition, because you have to, whenever you multiply, you have to add the multiply the corresponding elements and add them up. So basically these will be included here itself. So you require to have a matrix multiplication. Multiplication includes the multiplication of the corresponding elements and then add them up. So therefore it does not matter. So the addition operation is included into the matrix multiplication subroutine. So you require only these four operations, four subroutines to compute the solution vector x from a set of algebraic equations. Now that completes the method how to compute the solution of set of non-homogeneous algebraic equation using the eigenvalue problem, whatever we have discussed in the last few classes. Now if you remember, how will you solve a set of non-homogeneous algebraic equation? Probably if you remember Gauss-Seidel algorithm or by Gauss elimination method, one can compute either analytically or numerically. If it is a large dimensional problem, it is easier to go for numerical techniques. Now for implementing Gauss-Seidel algorithm, the major problem or the major barrier one will face is getting the inverse of the matrix. So that becomes a very problematic thing. If the matrix is not well behaved or well posed, then the determinant, the matrix may be a singular matrix, the determinant may be tending to 0. So matrix inversion becomes a very big problem. It is a big challenge numerically for any for solving such set of algebraic equations. So but if you adopt to this method, one can do away with the matrix inversion and just using the algorithm for evaluation of eigenvalues and eigenvectors and simply matrix multiplication and transpose of the matrix, that will give you the solution vector, and one can just avoid the matrix inversion in this particular method, and you will be getting an elegant solution by using the eigenvalue problem for the solution of set of nonlinear set of linear algebraic equations. Now I will take off couple of examples to demonstrate this method. The first example that I will be talking about is solution of the problem A x is equal to b, where I will be taking a very simple problem in order to demonstrate. Otherwise, if it is I will be taking a 2-dimensional problem for demonstration purposes. For higher dimensional problem, one has to go for the numerical methods to get this. Now all these subroutines that I was just talking about in order to solve this set of equations, the eigenvalues, eigenvectors, conversion from A to A transpose, multiplication of the matrices, all these subroutines are, you need not to write your own code. These subroutines are always available in the numerical recipes, either in they are available either in Fortran or in C++, or one can use the MATLAB code to connect all these routines together and can get the complete solution numerically. So you need not to write your own code. You can invoke these subroutines either from libraries or MATLAB, or you can join them up to get a complete solution. So for the demonstration purpose, I will be taking up this example A x is equal to b, where the elements of A are -2 and 2, 1 and -3, and solution matrix, the solution vector x will be composing of 2 elements x1 and x2, and b will be composing of -1 and 0. So So, basically the chemical engineering system will be described by 2 x 1 plus 2 x 2 is equal to minus 1 and x 1 minus 3 x 2 is equal to 0. The chemical engineering process will be having two unknowns, and these two unknowns you will be requiring two equations to solve them uniquely. So, therefore, these are the model equations to represent the chemical engineering problem, and probably this chemical engineering system is operating under steady state. So, we model the equation model the system by writing these two equations. So, these two equations can be written in a compact matrix form in the form of X equal to B in this fashion. Now, our aim is to find out what are the solution vector x 1 x 2 like that. In this case, since it is 2 into 2 matrix, we will be having only two elements in the solution vector x 1 and x 2. So, our aim is to obtain x 1 and x 2. So, first step, lambda i's, we find out the eigenvalues of matrix A. Evaluation of eigenvalues of matrix A. So, how to evaluate them? You can evaluate by computing determinant of A minus lambda I is equal to 0, and if you remember that minus 2 minus lambda. So, it minus 2 minus lambda 2 1 minus 3 minus lambda, that is the determinant of A minus lambda I, that should be is equal to 0. So, if you open up this determinant, this into this minus this into this. So, it will be 2 plus lambda minus minus plus. So, it will be 3 plus lambda minus 2 will be is equal to 0. So, it will be a quadratic, it will be 3 into 2 6 plus 3 lambda plus 2 lambda 5 lambda plus lambda square minus 2 is equal to 0. So, you will be getting lambda square plus 5 lambda plus 4 is equal to 0. This is a quadratic equation. It can be, you can get the roots as lambda plus 4 into lambda plus 1 is equal to 0. So, two eigenvalues are obtained as minus 4 and minus 1 in this case. So, the eigenvalues are lambda 1 is equal to minus 4, and lambda 2 is equal to minus 1. Now, we get the eigenvectors. Corresponding to lambda 1, you will be having the eigenvector x 1. So, A x 1 will be nothing but lambda 1 x 1. So, A minus lambda 1 I x 1 should be is equal to 0. So, what you will be getting is that I am writing the elements of this matrix minus 2 minus lambda 1 2 1 minus 3 minus lambda 1, and the elements of the eigenvectors are x 1 and x 2, and that will be equal to 0. Now, if you put lambda 1 is equal to minus 4, you just write. So, let us write these elements of this equation of this matrix 2 2 1 1 x 1 x 2 will be is equal to 0. So, therefore, we constitute the corresponding two equations 2 x 1 plus 2 x 2 is equal to 0, x 1 plus x 2 is equal to 0. So, they are giving basically identical solution. So, you have to just assume one value. So, if x 1 is equal to 1, then x 2 is equal to minus 1. So, 1 minus 1 will be one of the eigenvectors corresponding to the eigenvalue lambda 1 is equal to minus 4. So, therefore, x 1 is nothing but 1 minus 1, that is the solution of this set of equation. So, 1 minus 1 will be the eigenvector corresponding to lambda 1 is equal to minus 4. So, we write it down more explicitly. So, x 1 is equal to 1 minus 1 is eigenvector corresponding to eigenvalue lambda 1 is equal to minus 4. Then we compute x 2, the eigenvector corresponding to lambda 2 is equal to minus 1. For lambda 2, next eigenvalue lambda 2 is equal to minus 1. So, again we formulate a minus lambda 2 I, formulate the eigenvalue problem I x 2 is equal to 0. So, this will be minus 2 minus lambda 2 to 1 minus 3 minus lambda 2, and again the elements will be let us say x 1 x 2, that will be equal to 0. So, you will be getting minus x 1 plus 2 x 2, you put the value of lambda 2 as minus 1. So, you will be getting this minus 1 plus 2 x 2 will be equal to 0, x 1 minus 2 x 2 is equal to 0. So, again they are given identical, they are identical. So, if x 2 is equal to 1, then x 1 will be is equal to 2. So, therefore, two 1 is eigenvector corresponding to lambda 2 is equal to minus 1. For the eigenvalue as minus 1, the corresponding eigenvector is 2 1. So, we have found out the eigenvalues and eigenvectors of A. Next step is evaluation of eigenvectors of A transpose. Now, we have already seen that eigenvalues are identical for a matrix A and its transpose matrix A and A transpose, but the eigenvectors are different. So, therefore, in the next class we will be looking into how the eigenvectors are evaluated for A transpose, and the rest of the solution follows, and we will closely look into the solution step by step and complete the problem in the next class. We stop this class here, and we will start the next class after few minutes. Thank you very much.